With the interest of time, we go to the next speaker, Dr. Varun Dwarka. Varun Dwarka is a bioinformatician. He's an expert in aging and longevity research. He focuses a lot on genetic and molecular aspects of aging. He has extensive experience in this area. So he's speaking about the potential biomarkers of longevity. I let Dr. Varun take over.
Thank you, everyone. And to the organizers of Longevity Asia, thank you so much for this invitation. So my name is Varun Dwarka, and I serve as the Director of Bioinformatics and am a Principal Investigator at True Diagnostic, which is based in the United States in the state of Kentucky. And so I'm actually going to go a little bit different here because while I was thinking about going through all of the potential biomarkers, I'm actually going to be thinking a little bit more on the application and especially how we as a company are taking the science to the consumer and the researchers. And so the title of my talk will be using AI and ML to develop the most predictive and clinically informative epigenetic measures. And so to introduce me, I have to introduce the organization that I represent. So True Diagnostic, our vision is just to provide the best aging and clinical medicine insights via epigenetic methylation while collecting extensive covariate data and forming the largest phenotypic, multi-omic, and epigenetic database platform in the world. We've been around for only 3 years, and in that time, we have our own lab, so we are generating, pumping out a lot of methylation, DNA methylation data. We have actually 13 countries of distribution, and one country that is near and dear to my heart is my motherland of India. And so that is one of the places that I'm trying to really tackle. We've been able to publish 20 or more papers in the short 3 years that we've been around and have filed about 10 patents and have multiple collaborators all across the world. And so why do we do this? It's because the main reason is to collect the data, and this data is what facilitates the research that we do, and specifically this research that my lab does. And so even though it says 100,000 patients, this is actually a more culmination of 50,000. And we actually have longitudinal data. So the reason why all this is important is because of the metadata that we collect. This includes variables such as cancer diagnosis, Alzheimer's, depression, HIV, even lifestyle ideas where it comes from alcohol consumption and all that. The reason why all of this is important is because we are using this metadata as a way to train different AI and ML models using DNA methylation as the baseline. And it's through this that we've actually been able to commit in a large amount of resources towards the research. And so this really, a lot of our work has actually been published in Nature Aging, Genome Medicine Frontiers in Nutrition, and Aging itself. And so while I will go through a lot of slides, and especially in the context of summarizing the application, please contact me if you want the direct publications. And so to kind of start, I'm going to start with a short background. What is the science that facilitates all of this research and the IP that we develop? To do this, we have to understand the central dogma of molecular biology, where we have to understand how the DNA is organized in chromosomes and the relationship it has to epigenetics, not the genetics, but the relation to epigenetics. If you're familiar with epigenetics, there are multiple types. There's chromatin modifications or histone modifications. There's DNA methylation and non-coding RNAs, where these RNAs that don't actually code for messenger RNA are able to come back and actually regulate the gene expression. But the biomarker that I will be focusing on is DNA methylation, where these are methyl groups added to the cytosine or the Cs of the DNA, which then are there to popular school of thought is that the addition of that DNA methylation is able to hinder gene expression. And as you remove those methylation groups, then you can start to express the gene. And this is also dependent on the location. Typically, the understanding is that it happens in really functional areas, such as the promoter region. And so using DNA methylation, the reason why we focused on this as a biomarker is understanding the effect of the epigenome based on the environment. So based on nutrition, stress, toxicants, pathogens, and other environmental cues, that tends to affect the epigenome, which then is in part regulating the genes. Now, if you compare this to other tests such as that maybe use the genome, so like genomic or genetic tests, you have to understand the difference here. When you do a genetic test, and I'll label 23andMe, I'm not saying anything bad about them, is that a genetic test is very important because you take one test and you understand what your predispositions are. But the problem here is that with age, you can understand a predisposition, but age is not a static thing. It's a continuously changing alternative. And so with a genetic test, while it is important to understand predispositions, that genetic information hopefully is unchanging. You're not seeing major changes in your genome. And there are also few interventions to change genetic risk. Of course, we have things like CRISPR-Cas9 that are really becoming science fiction and really being starting to implement. But CRISPR is not anywhere close to being used on human, on especially adult humans. And so really understanding how the regulation of that genetics is very important. And this is where epigenetic testing is really going to be coming into play. The idea here is that patients can retest and manage progress several times across the lifespan. There are many interventions that actually affect epigenetic risks or changing epigenetic risks, specifically by hitting DNA methylation. And while some of those signals are inherited, especially when you think about certain genomic regions, majority of your DNA can actually be changed based on just environmental cues and also lifestyle changes. And that's where we are existing as a company. And so what can you calculate? So using DNA methylation, what are the aspects that you can look at? You can actually look at methylation QTL variants. And so this is really looking at the results and differences in DNA methylation across individuals associated with polymorphisms. You can calculate age, biological age, which is what I'm going to be focusing on today at some probes, which are altered throughout the life course. So it's not your entire DNA, it's more specific locations. You can look at cell type specificity. You can deconvolute from whole blood individual cell types. You can look at exposures. So using DNA methylation, what is your exposure rate to different for alcohol, for smoking, and other exposure rates, including pollution. And one of the most important things is it's outcome associated. DNA methylation can be causal or consequential to disease states, which makes it a great biomarker to look at association to disease. And so how do we turn this into a test? So what we do as a company and is following very much the research route. So what we do is that we send a kit out. Individuals are able to extract their blood, send it back to our lab. In our lab, we are able to extract the DNA, undergo bisulfite conversion, and then use the Illumina Epic 850K array. This is a research tool that I'm sure many of you are familiar with. If you are not, please email me. We can talk a little bit further. But the idea is that by using the 850K Epic V2, which is looking at about 900,000 CPGs at a single time, we can actually estimate the probability of methylation at individual CPG sites. Now, this is where the fun starts, and this is where really my team is kind of coming into play, is that by using these CPGs, we can train it to different outcomes. So whether it be chronological age, disease probability, or any other type of output, we can identify which CPGs are highly predictive of that outcome. And it is under this guise that we are able to build AI and ML models so that once we build the model that is highly predictive of that outcome, we can then reverse engineer it anytime that we get a new sample. So for example, here, even something so simple as, does this person have COPD, yes or no, or 1 or 0, we can create a classifier that way. And so with that said, I'm going to introduce the main use case. And this first section is going to be a little bit longer, but it's going to go through at least one of the clocks that we have developed. So the concept here is really understanding the difference between biological age and chronological age. And why are we focusing on aging? Well, if you think about it, the progression of aging is really the significant driver for disease risk. A lot of diseases are driven by the fact that you are aging at a higher rate. But the problem is this: people think that the older you are chronologically is the reason why you are getting more disease risk. While that is somewhat true, there are individuals that, let's say at the age of 45, if you are taking care of yourself, your biological age or the age of your organ systems, your cells, may actually be lower than your chronological age, which is likely because you're not imparting a lot of aging effects onto yourself. And so really understanding this biological age becomes a better determinant of your overall success as a human being and in the aging realm. And so really quantifying biological age is going to be very, very helpful. And epigenetics seems to do a very good job. So if you, let's say you calculate biological age using these epigenetic markers, let's say you are higher in your biological age than your chronological age. What we know, and this review here is actually a very good review that really looks at it, is that your all-cause mortality increases, your cancer risk increases. Things like stress can cause that age to be higher up. But then if you want to get lower age deceleration, as we call it, biological age deceleration, this could be due to the fact that you're taking in healthier food, you're exercising, and you could look at supplementation, which is then decreasing this age. And so this now becomes an internal tracker, very similar to a Apple Watch, but now this is a molecular tracker. And so how we've developed our first clock, if you will, we call these epigenetic clocks, is that we wanted to look not only at epigenetics, but incorporate different layers of aging biology. So molecular biology is not just one thing, it's multiple things. You have your epigenetics, your genetics, you have your transcriptomics or your transcriptional gene expression, and you have metabolites. And so that's what we did. In collaboration with Harvard Medical School and Mass General, we actually created a data set of individuals from the Harvard Medical School database through Mass General, and and essentially looked at methylation using the 850K array across 5,000 individuals. Of those 5,000, 1,500 we did proteomics using the SEER platform. We extracted their clinical data through EMR, and also their metabolite information was collected using Metabolon, the metabolite platform. So in order to do this, what we actually did was we developed our own internal EMR age. This is a age that is based on EMR data. And the way that we trained it was that looking at 61 different clinical phenotypes across 60,000 samples, we actually used a Cox regression model to identify which of these 61 were highly predictive of time till death. This is the time that of all those individuals of when they passed away. And then using this information, we predicted which of these would actually be very good at predicting somebody's time till death. And so we actually created our first model using EMR age. But the problem with this is that you don't actually, like for an average consumer, getting their EMR data is very, very hard. And so as a company, we do a lot of DNA methylation. So how do we convert this to something that is more usable for us? And that is where we actually trained everything to DNA methylation. But the cool thing here is that you can also not only train DNA methylation to age, we can actually use DNA methylation to estimate different protein levels, different clinical levels, and different metabolite levels as well. And remember, we collected all of this matched to methylation. And so what we did was we created about 396 models where each individual model is able to predict a protein, a clinical value, or metabolites. And what we did was we used lasso penalized regression, where we essentially just identified which CPGs are able to accurately and predictively predict the protein, clinical, and metabolites. So we actually created all of these models as well. And last but not least, we put it all together. Now we created this EMR age. This is an age measure based on EMR data. And now we trained all the methylation data, all the estimates from methylation for the proteins, clinical, and metabolites. And notice, we also created in a different paper, a 12-cell immune deconvolution, meaning from whole blood without using FACS sorting or any kind of cell sorting, we can estimate the relative percentage of these 12 immune cells. And all of this was combined and trained against EMR age to create this value called omic MH. Now, this is all fantastic from a methodology perspective, but how does it work? Because in the end of the day, we care about the people that are using this. And what we see is that this measure is actually very clinically relevant. What you're seeing here are the prevalent cases and incident cases. And what I'm doing is comparing all of these to previous epigenetic clocks. We're not the first company to create this, or sorry, we're not the first research group to create this, but we wanted to benchmark this against existing clocks. And what we see is that what we created outperforms every other epigenetic clock that is out there in the context of associating to disease. So for example, all-cause mortality, what you're seeing here are the hazard ratios. The more right they are, the more relationship there is to that value to that disease. So all-cause mortality, type 2 diabetes, stroke, depression, COPD, and cancer, meaning as the omic M age is higher, that the estimation or the association to that disease is stronger as well. But what's more important is the 5-year survival and 10-year survival. So what we did was we predicted whether an individual that has a higher, let's say, a higher value, omic age value, does that predict whether that individual will survive or not in 5 or 10 years? And what we see is that the AUC, or the percentage of predictiveness, or the essentially a value to show how predictive that measure is quite high. It's at 0.894 or 0.889. A value of 1 means perfect prediction. But when you compare it to, let's say, chronological age, this is your chronological age, you could see that it's more predictive than just looking at their date of birth or any of these existing epigenetic clocks. And so with this, we're very excited because we seemingly created a measure that was highly clinically relevant and is able to predict survival and other diseases. And so the next question is, how do you take this to the consumer? And so what we do is we actually created a report where we could tell you your omic M age or your epigenetic age compared to your calendar age. And because of all of these models or these associations, we could predict the risk of disease, such as mortality, COPD, cancer, depression, again, using the same type of modeling that's come from here. And then also what's really important is comparing it to the rest of our data set. We've done this for 50,000 patients. So now that individual can use that measure and compare against the rest of the population. I will say, because this is an American company, a lot of our users are majority from America, but what we're trying to do, and this is a huge part, is to kind of bring it to the Indian subcontinent. And that's actually been a passion of mine here as well. But what's important is that not only can we give you a overall score, but remember, we have models to also estimate individual proteins, those metabolites, and those clinical values without actually doing additional blood work. And so that's also additional insight that we could provide to the consumer just based on using those individual metrics that go into the overall multi-omic clock. And if you have any questions, please let me know. We can email after the presentation if you want to know more about that. Now, that is one flavor of the clock. We actually have other flavors. I will go through these slides a little bit more quickly. However, I want to make sure that I touch on how these use cases can be also used in different settings. We also have organ system specific clocks, meaning, so this paper came out from Morgan Levine's lab at Yale University, and we work closely with the lead author, Raghav Sehgal. And what we've actually been able to do is license systems age, which is essentially using blood as a surrogate. You can estimate age from other tissue types. And the reason why this works is, if you think about it, blood is a circulatory tissue and is able to go through all of these different organ systems. And so therefore, it's capturing different methylation states from these individual organ systems as well. And so using that kind of philosophy, we were able to train a lot of these, using blood as a surrogate, using blood in the matched organ, be able to understand which of the CPGs are able to capture the aging process using different age-related biomarkers from individual organs, and then turn that or deconvolute that into blood. And so now what we can do is, by taking blood, we can estimate those aging biomarkers and give a aging score or an age for individual tissues, or sorry, individual organs. And so how we do this for the consumer is that what we can now tell you is not only look at overall age, your like overall symphony age, we can then deconstruct it based on, okay, you're 45 now, but based on those lung biomarkers, you're 38, 44, 40, and then 49, 42, based on individual organ systems. So you're taking an overall score and now decomposing it to something that is a little bit more manageable for the consumer to understand. So let's say if this person wanted to decrease their age, it seems like their musculoskeletal age is actually the highest. So then they can work on different ways to decrease it. And that aspect is something that we're still working on at True Diagnostic with our clinical team. But last but not least, we also look at the overall pace of aging clock. If you are familiar with this space, you will know this paper by Daniel Belsky, who again is another collaborator of ours from from Columbia University, and Terry Moffat from Duke University. But the idea is this: all of the other clocks are showing an amalgamation or a combination of your current and past health. But for somebody, let's say, that's recovering from, let's say, alcohol use and wants to make a change in their current life, they need an estimate that is more proper for now, because they might score higher based on all the damage that they've done in the past. And so in order to maybe create a clock that is more representative of your current state, what these individuals did was that they actually used a cohort of individuals from New Zealand, from Dunedin, New Zealand, and they tracked those clinical values across a longitudinal cohort, looking at 19 different clinical values. So starting from their birth at 19 in the year 1972, all the way until more recently, 2018, they were able to use all those clinical values and create a single pace of aging score using an using a I think it was a Cox proportional model, or a model of sort. But then using that pace of aging, they then transposed it to CPGs. Same way that we were able to do it for omic age, what they did was they calculated that pace of aging and then used an elastic net to identify which CPG sites are predictive of that pace of aging. So now you can use this epigenetic test to estimate that pace of aging. And what that number, or that predicted number, really means is it's a measure, is a value which describes the rate at which you're aging per year. So what that means is, for an individual like this, who has a Dunedin pace value that is 0.89, for every year that they're aging, they're only aging at a rate of 0.89 years. And again, so this is actually a snippet of what what we show for our customers. And this is where it really comes into play, not only understanding what their value is, but as people are going through different life stages, different interventions, taking different supplements, they could track how they're doing. So for this individual, they took the second test, things weren't going well, but then they come back down to 0.89. Now, compared to the first test, nothing has changed, but now they can realize, hey, what did I do differently in my second test versus now? And then they could use that as a way to kind of track their internal aging. What is really important, and this is where a lot of my team comes into play, is to test a lot of these measures. So even though we didn't create Dunedin pace, we really tested it. And so we actually published a paper in BMC Medicine about 2 months ago, in July 29th, where we actually saw that when you compare twins, where one twin is on a vegan diet and one twin is on an omnivore diet, the individuals who were on a vegan diet showed lower Dunedin pace values, meaning their pace of aging, their immediate pace of aging, was lower. And this was done in only 8 weeks. So now we're understanding what is affecting these clocks, especially with Dunedin pace. And this is why we really like this and why we license this or providing it to our customers. We also know that lower caloric restriction leads to lower Dunedin pace. This was done actually by Daniel Belsky's group and was published in Nature Aging. And what is really interesting is that things like PTSD and depression can also be attributed, or can lead to, or is associated with, higher Dunedin pace. So meaning now we're not just looking at diet, but we're looking at how that individual's mental state is now affecting that pace of aging, or that current aging process. And so now I hope you're starting to see how this can now become a clinically relevant tracker that is looking at current state of aging, along with the other two epigenetic clocks, which are showing more of a current and past aging process. Now, number 3, estimating age, and this is my last use case, estimating age related to disease. So why do we care about age? Age is honestly just a number to assess how much risk of disease you're going to get from a clinical perspective. So in all of these cases, the idea, or if we were to show this flow chart, we start with CpG methylation biomarkers to estimate all of these EBPs, or epigenetic biomarker proxies, or in a classic clinical case, you'll estimate somebody's CRP or plasma viscosity to estimate how much of their inflammation is changing. So CRP increases, you presume that their inflammation is increasing. And if that inflammation increases, then that means that either their diabetes, cancer, or asthma can increase. But as you can see, this is kind of a problem. You have multiple areas of connection, and it's really not specific. And so we realized that. So why are we estimating age? To look at disease. So why don't we just go directly to the disease itself? And so now we're rethinking a lot of our processes. And actually, instead of looking at just epigenetic age, we're also creating models where we identify CPGs that are directly estimating the risk of asthma, the risk of diabetes, and risk of cancer. And we're calling these methylation risk scores. We're not the first people to do it and from a research perspective, but we are the first people that are, or the first group that we're trying to take this more to consumers, and especially in the United States, be able to get FDA approval, which we're hoping to get in the next 3 months. And why is that? Well, if you think about it, well, I mean, here are some of the initial results. As I mentioned before, AUC is a measure to look at predictiveness. And as the closer you are to 1, the higher the prediction. And as you can see, compared to a cancer specific company, which is Grail, their average AUC across their different cancers are 0.81. However, even with our own cancer methylation risk score, we've improved it to 0.85. But that's not the only thing. The most important thing is that we're going beyond cancer. We're looking at type 2 diabetes, COPD, stroke, coronary artery disease, and most importantly, just like how we were looking at depression and PTSD, we have one for depression. And what we hope is that these tests are going to actually bring more insight into the health of individuals when it comes to things, to diseases or to disease states that have not been looked at really, or maybe in certain societies are still looked at as not important. Depression is one of them. And so using that kind of idea, we're hoping that this will make an impact, not only in society, but just overall health. So to summarize, to impact aging, we need diagnostics and treatment. Epigenetics clocks serve in this capacity. So we have been fortunate enough to contribute to a lot of these current epigenetic clocks because they are able to estimate epigenetic age, which is a surrogate of biological age. And these epigenetic ages are seemingly clinically relevant and predictive of disease and health. We can get resolution to the individual organ. So now we can understand not only overall age, but like we can look at more individual organ age and also the current pace of aging versus overall age or historic age. These epigenetic biomarker proxies, these which I kind of went through a little bit quickly, these are the estimates or surrogates using DNA methylation of those protein, metabolite, and clinical values can provide more resolution from DNA methylation data without doing additional testing. You don't have to do proteomics. You don't have to do metabolomics. And it also allows for low cost and easy collection methods. And from the same data set which generates biological age. So now you're not only understanding the biological age, you're understanding how these metabolites, those proteins and clinical values are contributing to that biological age. And last but not least, we are developing methylation risk scores, and this is possible because instead of directly estimating age, you can now go to the exact disease and estimate age-related disease risk. And in closure, I'm just going to talk a little bit about the offerings. So I only looked at 3 of the offerings that we have, but we've used the same kind of idea or the same type of philosophy to look at skin clocks, looking at different clocks, epigenetic clocks based on repetitive regions like ERV and line 1. We have publications on all of these. We even have a P16 T cell senescence predictor as well. And for those individuals that are getting into bioinformatics but do not have coding experience, we've actually developed our own software to help with this epigenetics analysis. And so it automates EWAS, DMR, DML studies, epigenetic clock analysis. So all the clocks and algorithms are now stored in this program and is available to you if you are wanting to use EPIC v1, EPIC v2, or MSA methylation array data. And the most important thing for me is to bring these costs down so that places that are maybe not wanting to spend the incredible amount of money to be able to bring all of this technology to average consumers. And so what we've been doing is working with Illumina to create an MSA-specific algorithm. And what this is hopefully going to do is cut costs by 50%. And so areas of the world that need those cost reductions can now still have the same technology available, especially in their clinics. And with that said, thank you for your time. Please email me at varun@truediagnostic.com or link with me on LinkedIn. And yeah, happy to take questions here or on email. Thank you.
Fantastic. Dr. Varun. It was very exciting to listen to you and what you've been doing, and very exciting work coming out from what you have done, I think. So